Quickly Quantum. Oratomic says fault-tolerant, cryptographically relevant quantum computing might take just 10,000 qubits instead of millions. And today, a new paper from Caltech tries to prove the math behind that claim actually holds up. Does it? Before that, in the headlines, OpenAI says an internal model solved 10 long-standing open problems in math and quantum complexity for about $2,000 in compute. IQM posts its first earnings report as a public company. Rigetti and HPE get a name and $5 million behind their Pittsburgh hybrid testbed. And IonQ teams up with a Tennessee utility to launch a quantum communications research center wired into a live fiber network. Welcome back to Quickly Quantum, your daily brief on the quantum frontier. It's Tuesday, August 4th, 2026. Let's get into it. First up, IonQ and EPB, that's the Chattanooga, Tennessee utility, are launching the Tennessee Quantum Communications Research Center, a 5-year partnership wired directly into EPB's live fiber network. Here's what makes that interesting. Most quantum networking research happens on lab testbeds, isolated fiber loops built just for the experiment. This one's different. It's plugged into infrastructure that's actually carrying real traffic, so whatever they learn about distributing entanglement or securing communications has to survive the mess of a working network, not a sterile one. And analyst at Des Frontier Tech, also on X, flagged the commercial angle, noting the deal reflects, in their words, a shared commitment to turning quantum innovation into real-world economic and commercial value. We don't have hard numbers yet. Entanglement distribution rates, distances achieved, none of that's public. This is early days. But pairing trapped ion hardware with a utility's actual grid is a genuinely rare setup, and it tells you where quantum networking research is heading next. Story 2, and this one's a big swing. OpenAI says an internal version of its next model family, internally called Astra, cracked 10 long-standing open problems in math and theoretical computer science, including 2 with direct quantum relevance. The company put out a 249-page manuscript and a 62-page walkthrough of the model's reasoning, and, this is the number that stopped me, says the whole thing cost roughly $2,000 in compute. As OpenAI put it on X, quote, an internal version of our next major model produced 10 new results on long-standing open problems in mathematics and theoretical computer science, using roughly $2,000 worth of tokens at GPT 5.6 Sol API rates, end quote. On the quantum side, Astra reportedly proved exponential parallel repetition, a foundational question about how entangled quantum games behave when you play them many times at once, for every finite 2-player entangled game, and produced stronger hardness results for the closest vector problem, a lattice puzzle that underpins a lot of post-quantum cryptography. Researcher at Kenjatina Og summarized the spread on X, noting the problems span sphere packing, coding theory, quantum complexity, cryptography, and group theory. Here's the catch. Every proof comes with what OpenAI calls a machine-checkable lien certificate, lien being a formal proof verification language, which confirms the logic is airtight. What it doesn't confirm is whether the results are actually novel or significant. That's still an open question until the wider math and quantum complexity community gets to pick it apart. OpenAI hasn't released the detailed proofs for full peer review yet. Quick hit 3. IQM Quantum Computers just filed its first earnings report as a public company, and the numbers tell 2 different stories depending on which line you're reading. Revenue for the first half of 2026 came in at 8.9 million euros, against an operating loss of 60.5 million euros, so the losses still dwarf the revenue by nearly 7-1. But the number IQM wants you to focus on is the backlog. It grew from 69.1 million euros at the end of June to over 102.1 million euros as of early August, with 33 million euros added to the backlog since the end of June. The company's holding onto full-year guidance of 42 to 47 million euros in revenue, and says its 309.4 million euro cash balance buys runway into the second quarter of 2028. IQM's sold 26 full-stack systems, delivered 17, and is expanding into Japan and Spain. Backlog isn't revenue, though. It's a promise of future revenue, and analysts like Rothschild and company Redburn have stayed at a neutral rating, waiting to see those orders actually convert. Real progress, but the gap between backlog and bank account is still the story here. Over in Pittsburgh, there's an update to a story we flagged back in late July. The Pittsburgh Supercomputing Center's hybrid quantum classical build now has a name and a funding source. It's called Tangle Lab, and Quantum Computing Report reports it's backed by a $5 million NSF grant under the Advanced Computing Systems program, with Rigetti and HPE named as the hardware and infrastructure partners. We haven't independently confirmed this one yet, so treat the specifics as reported rather than settled, but the shape of it fits what we heard before. A joint Carnegie Mellon and University of Pittsburgh center building a testbed that pairs quantum processors with classical supercomputing rather than treating them as separate systems. That hybrid approach, quantum chips doing the parts they're good at, classical machines handling the rest, is basically the working assumption for how useful quantum computing actually arrives, and federally funded testbeds like this one are where that architecture gets stress tested outside a vendor's own lab. Last quick hit. Tokyo-based JIJ just pushed Chamomile to version 0.14.0, evolving what used to be a quantum optimization toolkit into a full, general-purpose quantum programming language. Developers now write Python-style code that JIJ says can algebraically calculate how many qubits and gates an algorithm actually needs, straight from the source code, then transpile that into other software kits like CUDA-Q or Qiskit. JIJ also closed a $5.2 million funding round, with backers including Global Brain and corporate investors like KDDI and Mitsubishi Electric, and landed a spot in Quantinuum's partner program. In a statement, the JIJ team said their goal is an environment where the language itself handles more of the underlying rules and complexity, allowing users to build quantum algorithms with greater confidence. It's not a flashy hardware story, but tooling like this is exactly the unglamorous plumbing that determines whether quantum algorithms actually get built by more than a handful of specialists. Our main story today, and I'm calling this one the 10,000 qubit question, because that's exactly what today's paper is trying to settle. Back in March, a neutral atom quantum computing startup called Oratomic came out of stealth with a genuinely audacious claim that fault-tolerant, cryptographically relevant quantum computing, the kind that could run Shor's algorithm, the routine that factors huge numbers, might not require millions of physical qubits like most estimates assume. Oratomic said it could be done with around 10,000. That's a massive drop from prior estimates, and it's not a small claim. It's the difference between this happens sometime after most of us retire and this happens on a timeline that actually matters to people running encrypted systems today. The claim was theoretical, cooked up by a team that includes Caltech's John Preskill, one of the founding voices of quantum error correction theory, along with Manuel Endres and Dolev Bluvstein, physicists known for neutral atom hardware, where individual atoms are trapped and moved by laser light like pieces on a reconfigurable board. Investors bought in hard. Oratomic raised a $300 million Series A in July, betting on that low qubit thesis. A big claim like that lives or dies on the error correction math underneath it, because quantum bits are notoriously fragile. Any stray noise flips them, and you need to spread information across many physical qubits to protect one reliable, logical qubit from failing. The codes that do that spreading are called QLDPC codes, Quantum Low-Density Parity Check codes, and they're the current best hope for doing error correction without needing an absurd number of physical qubits per logical one. Today's paper, out of Caltech and Oratomic together, introduces a new family they're calling mitten codes. The technical trick? These are built from non-abelian groups. That's math speak for symmetry structures where the order of operations matters, unlike the simpler abelian codes most QLDPC work has used. And that structure lets mitten codes dodge a ceiling that's been capping how good comparable codes can get. In the paper's simulations, a code labeled 36014, meaning 300 physical qubits protecting 60 logical ones, with a distance of 14 that determines how many errors it can tolerate, hit a block logical error rate of roughly 1 in 100 billion per round, at a physical error rate of just 1/10 of 1%. And in a decoder stress test spanning 15 billion simulated operations on a larger code, they saw only 2 logical failures. That larger code was labeled 540.108.18, 540 physical qubits, 108 logical qubits, distance 18. And the 15 billion trials tested something called lattice surgery, the technique by which you actually perform operations between different blocks of encoded qubits, which is where a lot of real-world error correction schemes tend to leak errors. 2 failures out of 15 billion attempts is the number behind the team's own claim that this points to a processor capable of roughly 10 billion logical operations before something breaks, with decoding fast enough, sub-millisecond, to keep pace with neutral atom hardware, which is exactly the platform Oratomic is building on. So on paper, mitten codes are a genuine advance in the error correction toolkit, not just window dressing for Oratomic's funding round. Quantum low-density parity check codes have been one of the field's most active research fronts precisely because they promise dramatically lower overhead than older approaches, and non-abelian constructions like this one have been a theoretical target for a while. The question the rest of this story has to answer is whether genuine advance in the math also means the 10,000 qubit claim survives contact with reality. So let's get into the deeper read. Does the math hold up? On the positive side, the pedigree here is hard to wave away. This isn't a random error correction paper. It's out of the group led by John Preskill, the Caltech physicist whose fault tolerance theory much of this field is built on, working alongside the physicists who built Oratomic's neutral atom hardware thesis in the first place. On X, patent attorney and quantum IP specialist @Michael Shallop captured the mainstream reaction, writing that, as @Preskill notes, practical quantum computing depends on advances in quantum error correction, and calling the mitten code work a significant step towards scalable, fault-tolerant quantum computing. And the raw numbers back up some of that enthusiasm. A logical error rate of 1 in 100 billion per round, and a decoder that failed only twice across 15 billion trials are not small results if they hold. That's the kind of reliability regime you actually need before you can trust a machine to run a computation that takes days or weeks of continuous operation, like factoring a genuinely large number. And zoom out for a second on why any of this matters outside a physics conference. Cryptographically relevant quantum computing is industry shorthand for a machine that can actually break the encryption protecting today's financial transactions, medical records, and government communications. The stakes of the 10,000 versus millions debate aren't academic. They're the difference between planning for this in the 2030s and planning for it now. But here's where I want to slow down, because there's a real gap between this math works in simulation and this machine exists. Every single number in today's paper, the error rates, the 15 billion trials, the sub-millisecond decoding, comes from circuit-level noise simulations, not a physical device. When Oratomic first emerged from stealth back in March with its original 10,000 qubit claim, Pasadena Now covered the launch and noted plainly that the results are theoretical. That description still applies today, and it's worth saying plainly, Oratomic is the company whose $300 million Series A was built on this exact narrative. That fault-tolerant, cryptographically relevant quantum computing needs thousands of qubits, not millions. So they have every incentive to keep publishing results that support that story, even if the results themselves are legitimate science. That's not an accusation of dishonesty, it's just an observation about incentives, and it's exactly why independent replication matters here more than usual. So where do I land? I think this is real, careful theoretical work from people with the credentials to do it right, and non-abelian QLDPC codes breaking past the distance ceiling that's limited earlier constructions is a legitimate advance the error correction community will want to poke at. But a decoder that never fails in simulation is a very different animal from a decoder running on real neutral atoms, where gate errors, atom loss, and measurement crosstalk don't behave like the noise model in a paper. The 10,000 qubit thesis hasn't been disproven today. If anything, the error correction machinery underneath it got stronger on paper. But it also hasn't been built yet, and until Oratomic or somebody else runs this on actual hardware, 10,000 qubits remains a very well-argued prediction, not a demonstrated fact. If I'm wrong about how skeptical to be here, the way I'd find out is simple. Somebody builds it. A physical demonstration, even a small one, a handful of logical qubits surviving lattice surgery on real neutral atoms, would move me a lot more than another archive paper with bigger simulated numbers. Time for the hype check. I'm giving this one a 6. The theory is genuinely strong and comes from people who know exactly what they're doing, but it's simulation stacked on top of simulation, funded by a company with $300 million riding on the answer coming out a certain way, and 0 physical qubits have actually run this code yet. The real test comes whenever Oratomic or an independent lab actually runs mitten codes on neutral atom hardware. That's the experiment that turns this from a strong paper into a validated architecture. And that's the number I'll be watching for next. If you're the kind of listener who wants the 10,000 qubit question answered the moment there's real hardware behind it, and not just another paper, Following Quickly Quantum wherever you get your podcasts means you won't miss it. If today's episode helped you make sense of QLDPC codes or Oratomic's bet, sharing it with one curious friend is the best compliment this show gets. This has been Quickly Quantum, an AI-voiced podcast, created and built by a real human using today's cutting-edge technology. Nothing you heard on this show is financial advice. I'm Brian Lampert, and I'll catch you all tomorrow. Take care.